Hello, everybody. Hey, this is going to be the vibrational motion quiz practice solutions, which is our penultimate quiz. In this problem, I made a slight technical problem here. So we're going to think of this spring is not going horizontally, but going up and down. And if you read the question carefully, it doesn't make sense if it goes horizontally. So we're going to do it this way. And I sent you a notice about that, but all the questions will kind of work out from there. So the first question is, what is the K constant? All right, so what we're going to do is we're going to put a 750 gram mass on the end of the spring. So the unstretched spring is 15 centimeters. And then when we hang the spring on there, then it is going to go to 55, which means that it's stretched 40 centimeters. Okay. So we're going to have F, which is mg down, and that is going to be equal to kx upwards. Okay, now we know that there is a negative on there, but in this case, the force is always in the opposite direction of the x. So essentially, the negative kind of disappears there. So we're going to have mg over x is equal to k, which is going to be 0.750 divided by 0.40, which is the difference between those. And then we also have 9.8. So let's calculate that. So 0.75 times 9.8 divided by 0.4 gives us a K value of 18. We're going to call it 18.4. Okay. So our K value is 18.4 newtons per meter. Okay. And that is the answer to question number one. Now, where is the equilibrium point? Okay, the equilibrium point, if we leave it this way, right, it's balanced right there. So question number two, the equilibrium point, or K naught, is equal at 55 centimeters. Okay. And then what is the amplitude of the subsequent vibration? So if you read the problem, once it's here at the equilibrium point, now we're going to stretch it until it is at 73 centimeters. So we're going to take 73 minus 55, and we're going to get an amplitude of 18 centimeters. So our amplitude is going to equal to 0.18 meters. Okay, that is our amplitude. Now we want to determine the angular frequency. This is much easier. This is much easier than it might sound. So number four, you may remember that omega, our angular frequency, is equal to the square root of k over m, which is going to be the square root of our spring constant, 18.4, divided by our mass, which is 750 grams, or 0.750 kilograms. So 18.4 divided by 0.750. And then we're going to take the square root of that, and we're going to get 4.95. Okay, so our omega is equal to 4.95. 4.95, and that would be radians per second, or seconds to the -1, or hertz, or whatever unit you like best for frequency. Okay, so now, you guys, we want to calculate the frequency, and this is going to be number 5. Now, the frequency is equal to, is it the frequency or the period? The period, sorry. And the period is equal to 2 pi times the square root of k over m. And you guys, I want to double check that to make sure I haven't flipped it, which can easily be done. So hold on, I'm going to find that and then check it. All right, I am back, and yeah, I flipped this over. So this is going to be equal to the square root of m over k. Now, we can just think of this as 2 pi over omega. And remember that if we switch these two, it's like saying that the velocity is equal to distance divided by time. So this is going to be our equation. So we're going to have 2 pi divided by our omega, which is 4.95. And let's calculate that. That's going to give us 1.27. So our period is equal to 1.27, and that would be seconds. And remember that I could ask you what the frequency is, which would just flip that over, which would give you like 0.79 hertz. Okay, so that is question number 5. Now we want question number 6. So calculate the total energy of the system. So remember, total energy is either going to be the kinetic energy or the potential energy. And it's a little, you guys, it's a little bit cumbersome. It's a little bit cumbersome to talk about the total energy when it's hanging straight up and down. Now, that force that's going up and down is a constant force. So we can from gravity. So we can just think of the spring and the kinetic energy, and we now know that the kinetic energy would be 1/2 mv max squared, because the velocity is going to be the greatest. The velocity is going to be the greatest right in the middle, and the potential energy is going to be greatest at the amplitudes. So we can say that this would equal to 1/2 k a squared, right? So it's either in the middle at the maximum or at the end at the maximum. And if it's in neither of those places, if it is neither of those places, then we can say it's 1/2 kx squared plus 1/2 mv squared. So the difference here is this is the position somewhere between plus or minus or 0 and plus or minus a. And here, this is V maxes, and this is just any old V. Now, since we know what the K and the A is, we can find the total energy by using this one. So we're going to say energy is equal to 1/2 Ka squared, and our K is 18.4. And our amplitude is, what was our amplitude? 0.18 squared. So 18.4 divided by 2 times 0.18 squared. And that is going to give us 0.298. We're going to call that 0.30. Okay, so the energy is 0.30 joules. That's equal to the overall energy, which is question number 6. Sorry. Yeah, so now what is the maximum velocity on the mass? So now what we're going to do, since we know that this is 0.3, we're going to set this equal to that. And number 7, so we're going to have 0.30 joules is equal to 1/2 of 0.75 times V max squared. So we're going to end up having here the square root of 2 times 0.30 divided by 0.75. And so that's going to give us a maximum velocity of 0.89 meters per second. And that is equal to V max. And that is question number 7. Question number 7. All right, question number 8. What is the location? What is the location when the mass is at half of its maximum velocity? Half of its maximum velocity. So essentially what we're going to say here is that our total, okay, and we're going to kind of use this, we're going to say 1/2 m V max squared is going to equal to 1/2 mv squared plus 1/2 kx squared. You guys, what we're doing is we are looking for that x. We want the location, okay? And we also know that this velocity right here is half of the V max, okay? So now we are going to say, well, actually all the halves can cancel out. So now we're going to have mv max squared minus mv max squared over 4, because this 2 would get squared, which makes it 1/4, which is going to give us 3/4 mv max squared is equal to kx squared. We're going to divide by k, and then we're going to take the square root, okay? All right, so now the square root of 3 times 0.75 times our V max, which is 0.89 squared, divided by 4 and divided by k, which is 18.4. All right, so let's calculate that. And we are going to get 0.155. So we'll call it 0.16. Okay, so our x is equal to 0.16. Now, you guys, that right there is going to be with relationship to our equilibrium point. So it's going to be plus or minus 0.16 on either side of the equilibrium point, which we know is at 55 centimeters. Okay, so we're going to say 55 plus 16, which would give us at 71, and 55 minus 16 would give us at 39. So we're going to, our real answer to question number 8 is going to be at 71 centimeters and 39 centimeters. Okay, so if we kind of look at our diagram here of our spring, right? So it's kind of going back and forth, and right there in the middle would be our maximum. But as it's going down, right, it's going to be hitting that 71 centimeter mark, which would be going at that point, and then it's going to go to the bottom and come back up, and it's also going to do that here at the top. So there's really four spots where it's going to hit that point. Okay, and now what is the velocity when it is at half its amplitude? When it's at half its amplitude. Okay, now so this is going to be very similar, you guys. It's going to be very similar to this one, and we are going to see 1/2 Ka squared minus 1/2 Kx squared is equal to 1/2 mv squared, right? So that's kind of that same thing, except this is the maximum is equal to this plus this. And now half our amplitude is going to be 1 or a over 2 squared, which again is going to give us 3/4 Ka squared. And again, those halves canceled out. And that's going to equal to mv squared. And then we're going to divide by m. And then we're going to take the square root. Okay, so we can see a very similar relationship there. But now the numbers are going to be slightly different. So we're going to have 3/4. This is 18.4. And our amplitude was 0.18. 0.18. That gets squared, and we're going to divide by 0.750. And so 3 times 18.4 times 0.18 squared divided by 4 divided by 0.750. And we're going to take the square root of that, and we're going to get 0.77. So that is going to be 0.77 meters per second is going to be our velocity when it is at half the amplitude. And again, half the amplitude is going to hit 4 different times, if that makes sense. Just same reason, because it's going through that cycle. All right, now we're going to now say that using up as the positive direction, write the equation for the position with respect to time. So we are going to use our standard equation, right? Our standard equation for this with respect to time is going to be x is equal to a cosine omega t plus phi, right? So that means that we would have started, you guys, up here, right? So if we use that as being positive, now we can just plug that in, except this amplitude would be negative. And so now we can have x is equal to negative 0.18 cosine. Now our omega was 4.95. So 4.95 t. And because we started at the very bottom, okay, that is going to be, if this stayed positive, then this would be pi. But since this is negative, we're starting at the bottom, and therefore our phase constant is going to be 0. Now, as far as you're concerned for the quiz, you don't have to worry about the phase constant because I'm not asking you about a question about phase constant. Okay, so it'll just be one of these standard sorts of things. All right, so now I'm using up as positive. Now we want to write the equation. Now we want to write the equation for our velocity. And so we're going to have, see, which question is this? So this was question 10. So question number 11, we're going to get velocity is equal to omega A sine omega t plus phi. We are going to get rid of that, and the derivative of cosine is negative sine, so the derivative of negative cosine would be positive sine. And now we're going to take our 4.95 times 0.18, our 4.95 times 0.18 is going to give us 0.89. So this is going to be 0.89 sine 4.95 t, and that's going to equal to velocity. Now, you guys, I want to point out that this omega A, that is your maximum velocity, which is what we get. Right there. Okay. All right. So that is question number 11. Question number 12 is going to be what is the equation for acceleration? So our standard equation for acceleration is going to equal to omega squared A cosine of omega t. Again, the derivative of sine is cosine, and therefore we're going to have acceleration is equal to 4.95 squared, 4.95 squared times the amplitude, which is 0.18, which is going to give us 4.4. So 4.41 cosine 4.95 t. And that is equation number 12. And now, if time is equal to 0 at the bottom and it was released, how long does it take to get to the 42 centimeter mark? Okay, so we know we're going to use this equation right here. Okay, and we're going to kind of shift over here. So remember, our amplitude is going to be, so we're essentially starting at the bottom. Okay, so we want x, and we're going to start at negative 0.18, negative 0.18 cosine of 4.95 t. Now, if we go up to 42, right, we're going to essentially say 55 minus 42. So that means we're going to go from negative 0.18 to positive 0.13. So this right here is going to be positive 0.13. Okay. So if we say 55 and we're going to go down 0.18, we're at 0.73. And if we go 55 and we go up to 42, the difference there is 0.13. Okay. So now what we're going to do here is we're going to divide both sides. So we're going to get 0.13 divided by negative 0.18, and that's going to equal to the cosine of 4.95. And we are going to take the inverse cosine of that quotient. So 0.13 divided by negative 0.18 is going to be negative 0.72. Now we're going to take the inverse cosine of that answer, and we're going to get 136. 136. And we're going to divide that by 4.95. And because when we take the inverse cosine, that's going to drop that out, and we're going to get t. And that's going to give us a time of 27.5 seconds. All right, you guys, that does not seem right. You guys, that does not seem right to me. So I'm going to stop and double check this and see what's going on. All right, as is usually the case, remember this has got to be in radians and my calculator was in degrees, all right? So when we take the inverse cosine of 0.13 over a negative 0.18, we are going to get 2.38. So 2.38. And now we're going to take that divided by 4.95, and we're going to get 0.48 seconds. 0.48 seconds. All right. So that looks a little bit better. So our time is equal to 0.49 seconds. Okay. All right. So that is question. Which question is that? That is going to be question number 13. And now we want to know how fast it's going when it reaches the 42 centimeter mark. And so now we're going to end up using, so this was number 13. And I'm going to get rid of some of this right here. And we're going to use our equation of velocity is equal to 0.89 sine of 4.95 t. Okay. And what is the velocity when it reaches the 42 centimeter mark? You guys, we don't see a x in this equation, right? So what we're going to use is we're going to use the time. We're going to use the time that we had from over here, which is going to be 0.49 seconds. Is going to be 0.49 seconds. All right. So now we're going to have 0.89 times the sine of 4.95 times times 0.49 seconds. Okay, 0.49 seconds, and that is going to be our velocity. And so 4.95 times 0.49 is equal to 4.24, and we're going to take the sine of that answer is going to give us 0.65, and now we're going to multiply that by 0.89, and we're going to get a velocity that is equal to 0.58, 0.85 meters per second. Okay, now you guys, it would then, if it's starting from the bottom and it comes up, once it reaches that 42 centimeter mark, it's going to be going 0.58 meters per second, right? Then it's going to reach all the way to the top, and then it's going to start its way back down. So when it reaches that 42 centimeter mark, right, it's going to be going 0.58 meters per second, but now it's going to be going negative. So that right there, you could really say plus or minus. But here we're just really talking about the first instant. Also, you guys, we could have calculated a second time for the same reason. As it went up, we calculated the time of 0.49 seconds to go from the bottom through the equilibrium until it first reaches 42 centimeters. It could go up and then come back down, and we would get another time. And that has to do with the fact, if you think about those things in terms of sine and cosine, that you have 4 quadrants. And so when you are taking sine and cosine, essentially they're giving you values that are in the first quadrant or relative to the first quadrant. So anyways, we want to now know, question 15, what is our acceleration when we reach the 42 centimeter mark? Okay, so this was problem 14. So now we're going to use our acceleration equation. So acceleration is going to equal to 4.41 times the cosine of 4.95. And again, we're going to use our time. We're going to use our time of 0.49 seconds. So 0.49 times 4.95 equals, now we're going to take the cosine of that answer, and now we're going to multiply by 4.41, and we're going to get negative 3.32, negative 3.32. So our acceleration is negative 3.32 meters per second squared. All right, so this might seem, you guys, this might seem a little bit odd, because how do we get a negative acceleration? All right, again, we started at the bottom here. And so in the first half up to the equilibrium point, the spring is going to be accelerating it upward in the positive direction. Now, once it goes above the equilibrium, now the spring is essentially pulling back. And so now it's going to have a negative force. So it's slowing it down on the way up. So that would, that's why we end up with a negative 3.32. Again, once it got to the top and it came back down on that same time as it went back down, we would end up having a positive 3.32. So 3.32 would work in both cases. But again, we were calculating it up based on our first equation of calculating the time to get to the 42 centimeter mark right only the first time. So we could have calculated it for the other ones. All right, hey, you guys, that is essentially the first half of this. I'm going to pause, erase this, and we'll end up doing the last part. All right. All right, ladies and gentlemen, 16 through 21 is dealing with a simple pendulum. So what we have here is a 1.5 kilogram mass on the end of a 36 centimeter long string, and it is displaced by an angle of 15 degrees. 15 degrees. And we are asked for determine the period of the pendulum. So the period of the pendulum is going to equal to 2 pi times the square root of L over G. Okay, so pretty easy peasy. And so we're going to have 2 pi times the square root of 0.36 divided by 9.8. And that is going to be 0.36 divided by 9.8, take the square root of that, multiply by 2, multiply by pi, and we're going to get 1.2. All right, so our period here is 1.2 seconds. And that is problem number 16. So problem 17, what would the frequency of this pendulum be if it were transported to the moon, where the acceleration due to gravity is 1.6. Okay, so essentially what we have here is we have the same equation, except we're just going to invert it. So frequency is going to be equal to 1 over 2 pi times the square root of g over L. Now, obviously, we could use that same equation, put in the gravity of 1.61, and then just get the answer and flip it over. But either way, so we're going to say 1 over 2 pi times the square root of 1.61 divided by 0.36. So the square root of 1.61 divided by 0.36 gives us 2.1 divided by 2 divided by pi. Okay, and we're going to get a frequency that is equal to 0.34 hertz. 0.34 hertz. And if we flip that over, we would get a frequency of 2.97. 2.97. So again, if we plugged in 0.36 divided by 1.61 square root 0.47 times 2 times pi. And so we plugged in 1.61 there, calculated, we would get 2.97 there. Okay. And then if we flip that over, we would get the frequency of 0.34 hertz. All right. So make sure when you're using these equations that you're getting either period or frequency depending on what I'm asked. Okay. So now, if the period for this pendulum was 3 seconds when it was transported to the surface of an unknown planet, what would the acceleration due to gravity be on this planet? So essentially what we're doing is we're going to find the equation for g, and then we're going to plug in our numbers and get that. So we can say that from here, we're going to get t squared over 4 pi squared, okay? And that would be equal to L over G, right? Because we squared everything. And now we want to flip this over. So we're going to have G is equal to 4 pi squared L over T squared. All right. So now we can plug in our numbers. 4 pi squared times 0.36 divided by 3 squared, right? Because that was the new period that it was asked for. So 4 times pi squared times 0.36 divided by 9, and that's going to be 1.57. Okay, 1.57 seconds. And that is equal to G. So now I didn't really mean it for this, but when you look at our period for the moon, that ended up being 1.97 when the acceleration was 1.61. So 3 and 1.57 kind of makes sense. This was not seconds. This was meters per second squared. Sorry about that. All right. Now, you guys, if we come back to Earth, all right, so we're basically back to here. And what would the frequency be if we doubled the mass? Now, if we doubled the mass, now remember, where do we see mass in either the frequency or the period equation? And the answer is we don't. And therefore, if we were to double the mass, it would not change anything. Okay, the frequency, which would be the inverse of 1.2, okay, which would be 0.833, that wouldn't change. Okay, now back on Earth, what would the period be if the amplitude was cut in half? So instead of being 15, now we're at 7.5. And again, it would not be affected. So the period is not affected by the amplitude. And if you've ever seen, if you've ever noticed when you have a pendulum, because of air resistance, it's going to slow down over time. But even as the amplitude gets shorter and shorter, the velocity slows down so that the period stays the same. All right, now back on Earth, what would the period be if the length of the pendulum was doubled? If the length of the pendulum was doubled, now we're seeing an effect. And so essentially what's going to happen is if we doubled the length and we take the square root of it, that means that the period is going to increase by a factor of 1.41, okay, which is the square root of 2. Okay, so we would have 1.2 times the square root of 2, which would be 1.7, okay? So the problem for 21 is going to be 1.7 seconds. All right, so that is problem 21. All right, so now we are going to go into our last 4 equations here. So I am going to pause and erase, and we'll get set up again. All right, ladies and gentlemen, for our last 4 questions, it says we've got a 500-gram mass placed at the 90-centimeter mark of a meter stick, and we are going to make this meter stick and mass a pendulum, right? Now, this is no longer a simple pendulum. This is going to be a physical pendulum, okay? And to calculate the period of a physical pendulum, that is going to equal to 2 pi times the square root of I over mgd. All right. So the first thing we're going to have to calculate is what is the I for this, and this is kind of where questions 22 and 23 are going to come into play. Now, from 16 on the the rotational equation, you were asked to calculate what is the moment of inertia of a meter stick, or actually, it was just a meter stick that's 1/5 in from the edge, and 1/5 of a meter stick is 20 centimeters. So it's essentially this equation to calculate the moment of inertia, and our equation was 13 ml squared over 75. So that's all we really have to do there in order to calculate what that is. So for 22, we're going to have 13 ml squared over 75, okay? So that's going to be 13 times 0.1, because the mass of the meter stick was 100 grams, times a length of 1 squared divided by 75. And 13 divided by 75 times 0.1 gives us 0.173. So our I here is going to equal to 0.0173, and that's kilogram meter squared. All right. Now, you guys, that's only part. Of our moment of inertia. Okay. So 22 says, what is the moment of inertia of this 500-gram mass with respect to the 20 centimeter mark? Okay. Now, we are just going to use mr squared for this one. So 23 I is equal to mr squared. We're just treating this as just a mass that's away from its axis of rotation. So this is going to be 0.5. Now, the distance from the 20 centimeter mark out to where the 5 kilogram mass is at 90 is going to be 70 centimeters, or 0.7, and that gets squared. Okay. So 0.5 times 0.7 squared is going to give us 2.45. Okay. So the I for 23 is 0.245 kilogram meters squared. And now, in order to calculate what that period is, we need the total I. So I technically didn't ask that, but you're going to have to use that anyways. So that's going to be 0.245 plus 0.017 plus 0.0173 is going to give us 0.262. So 0.262 kilogram meter squared. That's going to be the I that we use in our equation there. Now, we know what the mass is, we know what gravity. Now, this distance here is the distance from the pivot point to the center of mass, Now, if it was just the meter stick, that center of mass would be at the halfway point at 0.5. But we also have this, okay, which is way down at that 90 centimeter mark. Okay, so for question number 24, the center of mass, and we're just going to use X. It could be Y, doesn't matter. And that's going to be X1 M1 plus X2 M2 over M1 plus M2. Now, obviously, if we had more than two objects, we could just continue to go. All right, so now first the meter stick. And again, we know that the halfway point on the meter stick, because it's a meter stick and it's regular, the center of mass is in the geometric center, which is at 0.5. Okay, so it's going to be 0.5. Our mass is 100 grams, which is going to be 0.1. Okay, plus, now we know we've got 5 kilograms, okay, and it is at the 90 centimeter mark. So that's going to be 0.9 times 5. And our mass is going to be 5.1 kilograms. So 0.5 times 0.1 plus 0.9 times 5 is 0.45. And divide that by 5.1, and we're at 0.89. Okay, so our X center of mass is going to be at, you guys, I messed that up. This was not 5 kilograms, it was 500 grams, not 5 kilograms. Okay, so this was 500 grams. So that's just going to change this to be 0.5, and this is going to be 0.6. 100 grams, 500 grams is 600 grams. Okay, that's better. Let's recalculate that. Okay, so 0.9 times 0.5 plus 0.5 times 0.1 is equal to 0.5 divided by 0.6 is 0.83. 0.83, that makes more sense. Okay, 0.83. 0.83. So that is where our center of mass is, okay? And so our center of mass here is at 0.83, and the distance from 0.83 to 0.2 is going to be 0.63. So our D there is going to be 0.63. Okay, so now we can just plug in this equation, which is going to be 2 pi times the square root of our total I, which was 0.262, divided by our mass. Our total mass was 0.6 times 9.8, and that distance was 0.633. Okay. All right, and I'm getting 1.67. Okay, so our period, and this is question number 25, is 1.67 seconds. All right, now you guys, when you see a question like this, I will essentially be giving you that information. For example, I will tell you what I is and I will tell you what D is, and essentially all you have to do is plug it in. So there'll be many questions that we've seen on this review, the last review, and the review on gravity, where I'll give you some more information so it's not, it might not be as daunting to actually do the calculation. All right. All right. Until next time, we will see you.